All right, this is Computer Graphics Video 1. So I want to talk in this video about a little bit about the goal of this chapter and about linearity. So first, the goal. So what we want to learn how to do is basically deal with points in 2 and 3 dimensions. And so a little bit more than that, of course, right? Ideally, this is what we'd like. So we'd like to represent points by vectors. That's easy. And operations on points. This is the tricky bit. By matrix multiplication. So there are 3 operations we're interested in. That are quintessential for computer graphics. One is translation. So in other words, shifting a point. The second is rotation. This could be about a point or an axis, depending on the number of dimensions. And the third one is a perspective projection. Which is basically to turn a 3-dimensional picture into a 2-dimensional picture with a sense of perspective. So to turn a 3D pic into a 2D pic using a sense of perspective. And these 3 things we'd like to accomplish using matrix operations. So why matrix operations? Now, just to clarify what we mean by matrix operations, let me sort of give you an idea. Is let's see, what do we mean exactly? So, for example, could we find a matrix say M such that MP would rotate the point P around some other point? Let's say about, I don't know, some point. Doesn't have to be the origin, could be anything. Or could we find a matrix which translates, or could we find a matrix which does perspective projection, right? So again, why with matrix operations? So there are several reasons. First reason, computationally easy. Second of all, we can combine them. So let's say easy to combine. To see what we mean by that, we could say, for example, if M1 were to rotate and say M2 were to translate, then, for example, we could just do M2, M1P, and this would rotate and then translate. And that'd be really convenient. And lastly, if we want to operate on a bunch of points, what we can do is, let's say, to operate on lots of points, So what we do is we take those points, we pack them together in a matrix like this. Each point is a vector, and then we multiply by our m. And the reason this works is because the definition of this is the new matrix MP1 up to MPN. So we can do everything in one fell swoop. So since objects are made out of points, this makes it easy to work with objects in 3 dimensions. So this is the goal, is to try and figure out whether this is possible. So before we start actually hacking into this, what we'd like to do is talk next a little bit about linearity, which is connected to this, and to sort of do a brief refresher from basic linear algebra course about linearity, what it means, how it's related to vectors, etc. So let me clear the screen and do that. So linearity. So let's remember what it means for a function or for a transformation to be linear. So we'll say, suppose f from R, say, n to Rm. So all of our f's, all of our functions will be from either R2 to R3, or sorry, from R2 to R2 or R3 to R3, etc. But in general, suppose we have a function like this. So this is a transformation. Just think it's a function. So we say that f is linear if it has the following property. If f of alpha u plus beta b, or beta v, let's say, so we can split this up. Factor out the alpha and the beta, split it up over addition. This is the very definition of linear. Now, 2 things about being linear. Not going to prove these things. These are consequences that you study in a basic linear algebra course. So a transformation is linear if and only if it can be represented by a matrix multiplication. So in other words, right, i.e., there exists an n by, or an m by n matrix m such that f of u, to do f of u, we can simply take u and multiply by a matrix. So again, when I say fact, this is a theorem. This is a fairly complicated theorem. It's not obvious, but this is the practical upshot of it. Now here's the thing, right? If it is linear, there's like a nice rule for attaining this matrix. We can find m by calculating. So what we do is we take f and apply it to each of the standard basis vectors. That will do the job, right? So for example, let's actually do an example of something which isn't linear and an example of something which is. So the function f from R2 to R2 given by, say, f of the vector xy is, say, x squared y. This is not linear. And again, this is because in general, this fact does not hold. So for example, if I were to say f of 1, 1 plus 1, 1. If I calculate this, this is f of 2, 2, which is 4, 2. But if I were to take f of 1, 1 plus f of 1, 1, this would be 1, 1 plus 1, 1, which is 2, 2, and these are not the same. So there's an example that destroys the linearity. Now, something that is linear, something like f of xy is, say, 2x plus y and 3x. You can prove this simply by proving asterisk. I'm going to omit this for now. Just show this satisfies asterisk. It's not hard, it just takes a little bit of computation. And because it is, it can be represented by, so I could rewrite, or I could, in place of the way it's written, I could write this as m times xy, and the m that would do it is what I would do. I'd do f of 1, 0, f of 0, 1, f of 1, 0 is 1, 3, f of 0, 1 is, or sorry, f of 1, 0 is 2, 3, f of 0, 1 is 1, 0. So that's the matrix that represents this linear transformation. And so you can sort of see how this is connected to what we're looking at, because what we'd like to do, here's the connection right here. What we'd like to do is represent our operations by matrices, our geometric operations by matrices, which means they need to be linear. Right? So the practical upshot of that is thus. Our translations, or transformation, let's say translations slash rotations slash perspective projections need to be linear. Then and only then can we find matrices to represent them. Now, just as a side note, there's one more way to show that a function is linear, other than cutting to the chase and proving this equation. So let me just briefly clear the screen and say something about that, because that's the tack that we'll take, especially with the first example, and we won't do it every single time, but it'll be useful to keep it in mind. So note, two notes about linearity, really. So to prove f is linear, so we can go to the definition. Right, like you can just prove this. But this could be a bit unwieldy. So here's another option. What we can do is we can do the following. We can construct the matrix that we just showed and test whether the matrix does what we need it to do. Right? So in other words, we can construct this M. Right, so if we don't know it's linear, we could build this matrix and check if mx equals f of, or let's say we used a u, let's say mu equals f of u for all u. Right, if so, then f is linear. And M is its matrix. So one other note about linearity before we end this is that if f is linear, then just observe f of 0 vector. 0 vector is a 0 vector by plus itself, which is f of 0 plus f of 0 because of linearity. And if you cancel an f of 0 from both sides, so linear transformations take the 0 vector to a 0 vector. So keep this in mind because it'll be critical in a minute. Thus, if f of 0 is not 0, then f is not linear. Now, of course, note, keep in mind, if f of 0 is 0, this isn't enough for linearity. So the thing to keep in mind in this particular section then as a summary is we want to represent our operations by matrix multiplication. To do so, they need to be linear, which means they formally need to satisfy this definition. But that's an ugly definition to work with. So instead of that, what we could do is we could construct this matrix and check if that matrix does the same as our function. And if it does, then we have a linearity. And the second thing to keep in mind is if the function that we're looking at does not take 0 to 0, then it is absolutely not linear, and then we're out of luck. So keeping those things in mind, let's move forwards.